Hi, have you ever noticed how morning sunlight hitting a glass chandelier, a crystal ornament, or even the angled edge of a wall mirror casts bright, colorful patches of light across your room? Those aren't painted colors. They are hidden inside the light itself. Welcome to Chapter 6. Today, we are opening up a brand new unit, Spectrum. We're kicking off Section A by exploring how light behaves when it passes through a triangular glass prism. Let's get started. Deviation produced by a triangular prism. Imagine a single color, monochromatic light ray, PQ, striking the first surface AB. Because it's entering glass, which is a denser medium, it gets refracted and bends down towards the base, BC, traveling straight through as ray QR. This initial bend creates our first angle of deviation, labeled delta 1 at the first surface. Next, the ray hits the second surface, AC. As it exits back out into the air, it refracts again, bending even further towards the base as the emergent ray RS. This second bend gives us our second angle of deviation, delta 2. Now, if we extend the original path of our incident ray forward and trace our emergent ray backward, they meet to form the total angle of deviation, denoted by the Greek letter delta. Mathematically, the total angle of deviation is simply the sum of both individual bends. Delta equals delta 1 plus delta 2. Make sure you can draw this diagram perfectly for your exam. What determines how much a ray will bend inside a prism? There are three fundamental factors that dictate the total angle of deviation. Factor 1, the angle of incidence, I, at the first surface. Factor 2, the angle of the prism, A. This is the apex angle at the very top. A wider prism angle forces the light to bend more. Factor 3, the refractive index, mu, of the glass material. Different materials bend light differently. But wait, there's a hidden rule embedded in Factor 3. The refractive index of glass depends directly on the color or wavelength of the incoming light. Because of this, the final angle of deviation also changes depending on the color of light you shine through it. To understand this better, let's recall the formal definition of the refractive index mu. It is the ratio of the speed of light in a vacuum or air to the speed of light in that specific medium. In short, it is a direct measure of how much a medium slows down light. Now, look at the golden chain of cause and effect. If the wavelength of light is shorter, then its speed in the medium is also slower. When the speed in the medium is slower, the refractive index is higher. And a higher refractive index means the glass bends that light much more sharply. Let's apply this to the two extremes of visible light, red and violet. Violet light has a short wavelength of 4,000 angstroms. Because its wavelength is small, its speed in glass is the slowest. That means the glass presents the highest refractive index for violet, so the violet light is deviated the most. On the flip side, red light has a long wavelength of 8,000 angstroms. It travels the fastest through glass. Therefore, the glass presents its lowest refractive index for red, causing red light to be deviated the least. We saw how a glass prism bends different colors of light at completely different angles. But what about white light? White light looks boring, but it's actually a hidden bundle of 7 distinct colors: violet, indigo, blue, green, yellow, orange, and red. We can call it VIBGYOR by taking the first letter of every color. But why does your brain see them as different colors? It all comes down to wavelength. When these different waves hit the retina in your eye, your brain translates them into different colors. Wavelength is the ultimate characteristic of a color, no matter where it comes from. If you have red light from a cheap laser pointer, or red light from a giant star millions of light years away, if the wavelength is the same, your eye sees the exact same red. Now let's look at the wavelength and frequency of different colors. Don't panic about memorizing every single number in this table. You just need to spot the extreme limits to understand the pattern. Look at violet light. It sits at the short end of the spectrum, with a wavelength of just 4,000 angstroms. But because its waves are tightly squished together, it hits the absolute highest frequency at 7.5 times 10 to the power of 14 hertz. As you scroll down the table through blue, green, and yellow, the waves stretch out. The wavelength numbers get bigger while the frequencies drop. By the time you hit red light, you reach the opposite limit. Red has the longest wavelength, at 8,000 angstroms. But because its waves are so stretched out, it has the lowest frequency, at 3.75 times 10 to the power of 14 hertz. Now let's look closely at dispersion of white light through a prism and how it forms a spectrum. Back in the 1600s, Sir Isaac Newton was staring at planets through a lens telescope and noticed something highly annoying. The images had weird, colorful borders around the edges. At first, he thought it was just a cheap defect in his lens, so he made a perfectly polished, expensive new one. But the weird colors didn't go away. That's when Newton realized the problem wasn't the glass. It was the light itself. To figure out what was happening, Newton turned his lab into a completely pitch-black darkroom. He bored a tiny hole in his window shutter to let a single, narrow beam of sunlight pass through. He placed a glass prism right in front of that beam. When the light shot out of the other side and hit a white screen, it wasn't white anymore. It split into a beautiful rainbow patch, which he officially named a spectrum. The colors follow a highly strict order. Starting from the flat base of the prism and moving upward, the sequence spells out our famous word, VIBGYOR: violet, indigo, blue, green, yellow, orange, and red. From this, Newton proved a massive conclusion. White light is not a single pure color. It is polychromatic, meaning it is a giant mixture of many different wavelengths blended together. In a real spectrum, there are no sharp boundary lines separating the colors. Each color smoothly blends right into the next one. Now, let's check the definitions. First, dispersion, the phenomenon of splitting of white light by a prism into its constituent colors. Second, spectrum, the band of colors seen on passing white light through a prism. What actually causes dispersion? The cause of the dispersion of white light is the change in the speed of light with wavelength. Different colors travel at different speeds inside the glass prism. Because of this, when white light enters the first surface of a prism, light of different colors gets deviated through different angles towards the base of the prism. Violet is deviated the most, and red is deviated the least. This means that inside the glass prism, different colors follows different paths. When they strike the second surface of the prism, only refraction takes place. This causes the colors to separate out even more. The light emerging from the prism has the different colors spread out, which is what we see as a spectrum. So, what did we learn? 1. Dispersion happens at the very first surface of the prism. 2. Deviation happens at both surfaces of the prism. 3. The prism does not produce colors. It simply separates the colors that were already hiding inside the white light all along. With that, we have reached the end of part A of this chapter. Please hit that subscribe button. see you soon again in another video. Until then, bye!